So let's start with this example first. This example, we have an employee table, and how many records you have in this employee table? 5 records you have, and each record is of size 12 bytes. So the total allocation is 60 bytes. And I have another table, department table, and the employee table joins with the department table using the department number, and each record is of size 10 bytes. How I say 10 bytes? You can calculate 3 plus 4 plus 3, 10 bytes, and you have how many records? 4 records. So total allocation is 40 bytes. When I say allocation, it is allocation on the hard disk. Now comes a query. I have to execute a query which does this. Select employee name and department name from employee department table. The join condition is department number should be equal to department number and name is equal to Sam and department name is equal to SPST. So I am only worried about employees whose name is Sam and departments which has a name SPST. For these records I have to print the name and department name, that's it. So we went through this in the last class itself. So you give the query as input, the very first step it's going to scan, parse and validate. Then it will build an initial query tree. This is a tree data structure. This initial query tree is not an optimized tree. This query tree will be given to the query optimizer, which will apply the heuristic rules one by one on the tree, optimize it, generate the execution plan. An execution plan is what steps the optimizer takes towards executing that query. Once when that is done, this plan is given to the query code generator. Query code generator will generate the code and hand it over to runtime database processor, which will execute to give you the result. So we know optimizer optimizes the query. We are looking at heuristic query optimization here. So let's talk about how to build this initial query tree for our example. So what will be the leaf nodes in your tree? Your table should be the leaf nodes. So what are the two tables I have? I have this employee table and department table. You ignore all those things given in red, you just concentrate on this. What are the two tables we have? We have employee and department table. And what we are going to do is we are going to do a cross join of employee with department. So that is the cross join. On this cross join, you apply a series of conditions. What are those conditions? Department number of the employee table should be equal to department number of the department table. Department name should be equal to SPST and name should be equal to SAP. So you filter the Cartesian result and then you apply the projection. That is, you project only name and department name for every employee. So you call this the initial query tree that is generated by the parser. It is not an optimized tree. So what are the leaf nodes for your tree? The tables. And then you put a Cartesian product, put all the conditions and then the projection. So now we have to look into some statistics here. If I want to perform this, how many bytes I am going to access from the disk? What will be the size of the intermediate relation? All these things we have to focus on. Say when you talk about employee table, totally we have 60 bytes on the disk. 5 rows each containing 12 bytes. We have already understood that. And when you talk about department table, 4 rows each containing 10 bytes. So total is 40 bytes. So you have to access from the disk a total of 100 bytes. So when you do a Cartesian join of 5 rows with 4 rows, how many rows you are going to get here? 20 rows will be the intermediate result that is getting generated. And for each row, how many bytes you are going to have? That is 12 bytes plus 10 bytes. So you will have 20 rows each of 22 bytes. Your intermediate relation will be 440 bytes. So when you perform a Cartesian join of employee with the department, the intermediate relation is 440 bytes and the access is 60 and 40 bytes. We can go and view a query plan for any query that we are going to execute. I tell you how to view the query plan. How will you view the query plan? We have to use this utility explain plan. Explain plan for select star from M1 cross join F1. That's the plan. And let's go and run this query. Select star from table. Let's go to this plan of display. Okay. So you are getting the query plan here for the Cartesian product we have done. You can very well see what the optimizer has done here. The optimizer selects how many bytes from employee table? 60 bytes. Because it has to do a Cartesian product, access every record. How many bytes from the department table? 40 bytes. So you see here, the bytes access, number of rows access. So it's going to access both the tables, and what is the intermediate Cartesian product result in bytes? 440 bytes. So if you go and execute this query, you are going to get these statistics. So that's what is given here. So once when you get this Cartesian result, what is the Cartesian result you will get when you run this query? Say I just want to run this query, select star from M1 cross join F1. When I run this Cartesian product, what I am going to get? I am going to get 20 rows of data like this. On this, what I should do? I should apply these conditions and see. So when you apply those conditions on this particular Cartesian result you are generating, what is going to happen is you are going to get the table like this. And on this, what you are going to do? You are going to project name and department name. So you are going to have name and department name projected. That will be your final result. To come to this result, we have read 100 bytes from the disk and created an intermediate relation of 440 bytes. Then we apply the sigma and then the pi. So this is not optimized. Now the question comes into optimization, right? The question we ask is it possible to reduce the number of bytes we are reading from the disk? Should we read all the blocks for both the tables? Because it's going to take some I/O time. What is that? When you read a block, what is the time you are going to face? How will you calculate the total time required for transferring a block from the disk? What is the total time required for transferring a block from the disk to the main memory? It is seek time, rotational delay, and then block transfer time. So when you are going to read all the blocks, you are just going to have a delay there. So you have to read only the blocks that is needed. So how can you reduce the size of the data right here? So for that we go with a set of rules. These are the heuristic rules. The optimizer constructs that initial query tree and starts applying the rules. Rule 1. What is rule 1? You break any big selection condition into smaller chunks. So I have broken it down. First I am applying this. And then you think whether you can apply any one of the conditions on a table separately. What you have to think is, can you really move this down the tree? That is rule number 2. Rule number 1 is you break it down. Rule number 2 is try and move the selection conditions down the tree immediately wherever you can apply it. So from the employee table, I am only worried about employees with name Sam. So even before reading it from the disk, I will filter the blocks. So from the department table, I am only worried about departments with the name SPST. So what we can do now is, since we are filtering it out here, there can be a variation in what we are going to read. Earlier we read all the 5 records, now we are going to read only 3 records. Each record is of size 12 bytes from the employee table. So you are going to read 36 bytes from the employee table. Earlier we were reading 60 bytes, now it's 36 bytes. Likewise, in the department table, we are worried only about department names SPST, so we'll read only 2 records from the disk and it is of 10 bytes each, so we'll limit our read to 20 bytes. Earlier it was 40 bytes. This may sound very simple, right? 40 bytes, 20 bytes, what is that? You talk about you're running a data analytics query on a very large database having 4 million records, and you're worried only about department name SPST, which is of 1 million in count. So by just filtering 4 million records, you're just going to arrive at 1 million. You're going to eradicate so many blocks of read from the disks. This rule, though it sounds so simple, this rule actually saves a lot of time. So now what happens when you take a look at the statistics, we read from the employee table 36 bytes and we read from the department table 20 bytes. And how many rows in the employee table? 3 rows and 2 rows. And how many bytes you are accessing from the disk? Now it is reduced from 100, it is reduced to 56. And in intermediate result, how many rows you are going to generate? 3 and 2, Cartesian product will generate 6 rows. 6 rows each containing 22 bytes. So your intermediate result is now 132 bytes. So from 440, you have reduced that to 132 bytes. Why your intermediate relation size should be small? Is it good to have an intermediate relation that is of smaller in size? If your size is very small, then when you apply the condition and filter the rows, it's going to be faster, right? Because the Cartesian result you are going to filter. So that is also advantages. Your intermediate results also should be small. So what we get here is 132 bytes. See, I have run the query plan, I have got the result, I have just pasted it here. You can very well see in the query plan from the employee table it selects 36 bytes. And from the department table it selects only 20 bytes. And the intermediate relation that it generates is 132 bytes. So when it applies this heuristic rule, this kind of a reduction happens. So this Cartesian product, now it has got how many rows? 6 rows. Totally how many bytes? 132 bytes. So on this, if you apply the conditions, department number is equal to department number, SPST and employee name is Sam, you will get only this record where there is a match between department number and department. So finally, on this final result, what you have to do? We have to project name and department name. Again, you are ending up with the final result. In both the cases, we ended up with the same result, but then the number of bytes we accessed, number of bytes that we used, the size of your intermediate relation got reduced by applying a heuristic rule. So we applied just rule number 1, that is breaking your sigma into pieces. Rule number 2 is move that sigma down the tree. Rule 3 is, there is a rule 3. Actually speaking, we have a rule 3 that comes ahead of even this, but we will be looking at that in another example. For now, let us assume this is the rule 3. What rule 3 says is, wherever you have this Cartesian product, you convert that to a join. Why should we go in for a Cartesian product when we have a join? What this rule says, you take this Cartesian product, merge it with the step above. So you are going to merge these 2 steps and you are going to just get this step. This is a join. What join is this? Equi-join. So when you convert it to a join, instead of having 6 rows, you are just going to have 1 row directly. And it's a Cartesian join, we generated 6 rows. When you convert that to a join, it just match it using the department numbers, create 1 row direct. So from 6 rows, you have reduced it to 1 row. And these are the statistics we get. Say it reads 36 bytes for the employee table, 20 bytes for the department table. But now 132 bytes got reduced to 44 bytes internally. Just because you made it a join. You remove the Cartesian product and made it a join. So that is rule number 3 as of now. Wherever you have the Cartesian product, make it a join and write the condition out. You merge it with the sigma state. So this is what we get by applying a join, right? This is what we get. On this you are going to project name and department name. So you will project name and department name, you will get the final result. Applying rule number 3, again we are getting SAM and SPST to be the output, but our intermediate relation size is only 44 bytes and not 132 bytes. Rule number 4, you take a closer look at the employee table. What are the fields in the employee table? ID, name, department number and designation. There is a field called designation. Are we using this designation for any of our joins or results? We are not using this column anywhere, right? This entire column is not used for our computations. So we don't need to access or retrieve this. So if you filter this out, how many bytes will be left out? You are going to only read records of type SAM. So you are having 3 records. So earlier you were reading 36 bytes for 3 records. Now you are going to leave 3 plus 3 plus 3, 9. So how many bytes you are going to read? Because these things we don't need for our SAM. Did you all understand one thing? This particular column is not needed for a computation. So why to even read that or access that? Again, when you talk about department 1 table, this is department location. Is department location needed for our joins or for any of our results? No. So why did we even access this? So we are going to now leave out certain columns, that is designation and department location. So now we are breaking and moving the project operations down the tree. So what I am doing is, employee table at a total of 60 bytes. After I filter only for records of SAM, we read 3 records of 36 bytes. After we leave out, see I am leaving out another column to an employee. I don't need employee ID for anything. I am joining only with department number. So I am going to leave out employee ID and designation from my table. So what happens is, I am going to filter 18 bytes out by just leaving ID and employee designation. So what will happen after your project? You are going to read only 18 bytes from the disk. Because we don't need ID and designation anywhere, we filter that out. So you now reduce it to 18 bytes. From the department name column, say we are going to read only SPST and we are going to leave out the department location. So now from 20 bytes it is reduced to 14 bytes. I will show you the result. So this is what happens to the employee table. Leave out designation and ID and you have only records for SAM. So you have 18 bytes, 3 into 6, 18. Likewise for department table, you leave the department location and you filter only records for SPST. So you are going to get 2 records, each of 7 bytes. So you are going to get 14 bytes access from the disk. So when you project things out earlier down the tree, your size of the records accessed from the disk still reduces, number of bytes reduces. So from 36 it's now 18 and 14. And the intermediate relation size is now 26 bytes. It got reduced from 44 to 26. So this is the query plan for this. And you see here, the query will reach how many bytes from the disk? 18. And for the department table 14, an intermediate relation of 26 bytes. So you can now say this to be an optimized tree for our initial query tree, because from 440 bytes we have reduced it to 26 bytes. And rather than reading 100 bytes, we are just now reading 32 bytes from the disk. You will understand this. Now you are going to construct a query tree, initial query tree and an optimized query tree for this exercise. Display the name of all employees who work on a project by name OSP. I just need the employee names for employees who work on a project by name operating systems, OSP. So to get this, how many tables you have to join? You have this employee table, you have employee ID, name, department, and then designation. You have the works on table. So works on table, the ID is actually a foreign key in the works on table. SSN is mapped to ID. So this employee works on which project? So again, you need the project table. So project ID is a foreign key mapping to the project ID in the project table. The project name should be OSP. So we'll have this to be, say, OSP. So this is project ID actually, and let's consider this is some other ID, OSC or OSC, and project name is OSP. Again, this is OSC. So I'm just making a small change here. Since project name and PID is the same here, I'm just changing it. See, you can call the project ID to be OSC, project name to be OSP. So here in the works on table, you are going to have OSC and OSC. So what is our idea? Display the name for all the employees who was working on the project by name OSP. So you have to join this employee table with works on, find the corresponding project that this employee is working for, and then if the project name is OSP, you have to display the name of the employee. So how many employees are working for OSP project? 1 to 4. 1 to 4 is Tom. 1 to 7 is working, 1 to 7 is Sam. So your final output should be this. The examination question is construct an initial query tree and then optimize version of the query tree. No need to compute bytes or anything. Just construct the initial query tree. So what are the relations here? Employee 1 works on project. So what I will do is I will construct the initial query tree like this. Take all the relations. They all actually form the leaf nodes. So I will join employee with works on. That's a Cartesian product because it's an initial query tree. And then I will have this project. I will join this Cartesian result with the project. Employee with works on with project, Cartesian result. On this result, I will apply the series of conditions. What are the conditions? Employee ID should be equal to works on ID, and works on project ID should be equal to project's project ID, and project name should be equal to OSP. That is the condition. We filter rows. Finally, what we should project? Only the name of the employee. So to construct this query tree, you should be very good in joins and you should know relational algebra. The query tree is constructed internally using relational algebra. Please keep that in mind. These are standards we have to follow. So now let us go and take a look at our tables, our statistics just for understanding. Employee has got 60 bytes of information, 5 rows with 12 bytes, the same table. Works on table. What is this works on table? I just show you. Select star from works on 1. This table has got 6 records, each with 6 bytes. So how much you are going to read? 36 bytes from the test. So when you do a Cartesian join of 5 rows here with 6 rows here, how many intermediate rows you will get here? What will be the number of intermediate rows you will get when you do a Cartesian join? 30 rows. And then you have 30 rows here, that is the intermediate result. How many rows you have in your project table? So we have to go and check that. So if we go and check this, select star from project 1. So I have how many rows? 3 rows, 6 bytes each, so you have 18 bytes. So you are going to access 18 bytes and then you are going to create an intermediate result. So 3 rows here and 30 rows here. How many rows you will get in the Cartesian product here? 90 rows. I didn't calculate the bytes. Let it be 9. You know 90 rows is a huge data. So on this you are going to apply all these conditions. And then you apply the filter, you are going to get the result. What is the result? Tom and Sam. These two guys you are going to get. So how will you optimize this tree? Quickly think on the optimization. 4 rules you have studied. Rule number 1 is, you have this big selection, break it down into parts and then see whether you can move it down the tree. So if I break it down into parts, this is one part, this is one part, this is one part. So project name is equal to OSP. This one, I can move it down the tree, right? I am only worried about projects of name OSP. So I can go and filter it immediately. So that is rule 1 and rule 2 I apply. Now you go and look at the tree. The only thing is, from here I have moved the selection here. Because I am only worried about projects of name OSP. I am not having any selection on employee or works on. So it's going to be the same. So now let's go and take a look at the statistics. So when you are worried about only projects of type OSP, how many records you are going to have? You are just going to have one record for your project table. So from 18 bytes, it's going to reduce to 6 bytes and 1 row here. So here you have 5 rows, here you have works on 6 rows, you are getting 30. 30 rows, you do a cross join with 1 row, how much you are going to get? 30 rows. So by just applying this one rule, you have reduced from 90 rows to 30 rows. Then you apply the conditions and then you project. What is rule number 3? Here we are going to learn the actual rule number 3. I told you, right, there is another rule number 3. We are going to learn this too. We are going to take the restrictive select first. Rearrange the nodes such that the restrictive select happens first. So you go back, from the employee table, how many records you are selecting? 5. From the works on table, how many records you are selecting? 6. All the records you are selecting. But from the project table, out of the 3 records, you are just selecting 1 record. So there is a restrictive select on project, because from project you are filtering more records. So what is the plan is, you rearrange the leaf nodes such that the most restrictive selection happens first. So how will you go and rearrange the leaf nodes? So instead of so I'll just show you how I have rearranged the leaf nodes. Instead of having employee join with works on, I'm going to just join project with works on. Because project, I'm having a more restrictive select. I'm filtering more records. So from project, how many rows you have? 1 row. From works on, how many rows you have? 6 rows. Your intermediate result will now go to 6 rows. Just because you rearranged, from 30 you have now reached 6 in your intermediate relation. Now you have 6 rows this side, you have 5 rows this side, and Cartesian join will be 30. The same tree, when you, before rearranging the leaf nodes, when you take a look at the previous slide, before rearranging the leaf nodes, we have 30 records generated in the intermediate results. After rearranging, what happened? Your intermediate relation size went to only 6 rows. Got it? So now rule number 4. What is rule number 4? You replace all the Cartesian products with a join. So wherever I had the Cartesian product, I merged it with the sigma and then made it a join. So when you make it a join, what happens is, you will go with the statistics now. So whenever you see, after rule number 3, you are going to convert everything to a join. After you join, what happens? The number of rows generated for intermediate relation is 6 and then 2. In the previous step we had 30 rows. When you move it to a join, it becomes 2 rows. What is rule number 5? See whether you can really remove any unwanted columns. Move the project down the tree. So that is the final thing, and we don't have any projections here, because from employee Yeah, we have one projection here. From employee, we are interested in only ID and name. We are not interested in designation, or we are not interested in department number. So what is rule number 5? Move the projections down the tree. So we have arrived at a tree like this. Can we really filter out any unwanted records? Project table, we need both project ID and project name. We cannot filter any unwanted columns. Works on, we need both ESSN and PID, project ID, so we cannot filter anything. From employee table, we don't need department number or department designation. These two columns are not needed, so we are going to have a project here. So this is moving project down the tree. And that becomes your optimized query tree. See, this is a really a brainstorming activity. In the exams, don't be in a hurry to jump to results. Because more you analyze, more unwanted things will be skipped from your trees. And you have to construct the tree only in relational algebra. And no need to compute any bytes or anything. That is just for your understanding what is optimization. All these heuristic rules are based on general transformation rules. So what do you mean by general transformation rule? I will give you an example. R having an equijoin with S is nothing but S having an equijoin with R. So this is one transformation rule. Either you join S and R first and R and W next, or you join R and W first and S and R next. The result is going to be the same. So these are the rules. We already talked about commutativity of select operation, and then we talked about project. So you can go through the rules. When you see here, they say join, intersection, union, intersection, cross join, all these are associative. What is associativity? R theta S theta T is equal to R theta S theta T. No matter in what order you perform the operations, you are going to get the equivalence. So all the heuristic rules were based on these 10 transformation rules. I didn't go through every transformation rule, that will be very hectic. We have understood that directly from our slides. How did we understand that? Either you join employee with works on and then join with project, that gives the same result. Or you join project with works on and then with employee, you get the same result. So this kind of a change you can make because of the general transformation rule we have. Okay. So that's about our query optimization.